Hello students, through this simulation, we are going to see the relationship between potential difference and current flowing through a circuit. We have a circuit over here which contains a 1.8 volt battery and a resistor of value 76 ohm resistance. The current through the circuit is now 23.7 milliampere. Now let us see what happens to the current when we are increasing the voltage. Let us increase the voltage by adding more number of cells to the circuit. You can see here when the voltage increases, I also increases, current is also getting increased. The increase in current is represented by an increase in the size of the letter I as well as the arrow marks, which shows the flow of current through the circuit. When the voltage increases, the current also getting decreased. We can say that voltage is directly proportional to the current flowing through the circuit. Now let us see what happens, or what is the relationship between the current and resistance. When you are increasing the resistance of the circuit without changing the potential difference, you can see a decrease in the current. Now the letter R is increasing, so the letter I, which corresponds to the current, is decreasing. So resistance and current are inversely proportional, but voltage and current are directly proportional. When the resistance decreases, the current through the circuit increases. Thank you. Through this simulation, we are going to see the factors on which the resistance of a conductor depends. As you all know, the resistance of a conductor depends on four factors. One is the resistivity of the conductor, or the specific resistance of the material of the conductor, length of the conductor L, and area of cross section, or the thickness A of the conductor. And the fourth one is the temperature. Now here, the equation to find the resistance of a conductor at a given temperature, R is equal to rho into L by A, which shows that R is directly proportional to the resistivity, as well as it is directly proportional to the length of the conductor, and it is inversely proportional to the area of cross section of the conductor. Let us see what happens when we are increasing the resistivity rho of the material of the conductor. The rho here, now the value is 0.5 ohm centimeter, which is not the SI unit, but it's given in ohm centimeter. Let us see what happens to the resistance when we are increasing the resistivity of the material of the conductor. You can see here, when the resistivity increased, resistance also getting increased. When we are reducing the resistivity, resistance is also getting reduced. Now the second factor, the length of the conductor. Presently, we have taken a wire of 10 centimeter length. Now, what happens to the resistance when we are increasing the length of the conductor? You can see here, as the length increases, the resistance is also getting increased. And when the length decreases, the resistance decreases. Now the third factor, the area of cross section. Now we have a wire of 7.5 centimeter square area of cross section. Let us see what happens when we are increasing the area of cross section. When the area of cross section increases, the resistance is decreasing. And when we are decreasing the area of cross section, that means when the wire becomes thin, the resistance is increasing. So you can see the inverse relationship between area and resistance by this simulation. Thank you.